All of you knows that polarimetry, especially spectropolarimetry, plays an important role in modern astrophysics. Polarization observations can shed light on special distribution of matter around sources, magnetic fields, the radiation nature of sources, and so on. In the last year, different polarization techniques and devices are developed, and in the last year, especially polarimetry and spectropolarimetry observations of short-living and fast variable objects such as gamma ray burst and supernovae are very important. In my presentation, I'll talk about polarization measurements with MASTER Global Robotic Net. It's accuracy examination for different kind of astrophysical objects such as blazars and supernovae as an example. I'll mention about our polarization observation of GRBs shortly, because tomorrow Evgeny Garbovskoy, he is my colleague, will present a talk about prompt GRBs observations and in polarizers too. 2 days ago, on Monday, Denis Denisenko presented you our MasterNet, but I would like to remind you that MASTER is a mobile astronomical system of telescope robots, and polarization measurements was one of the reasons for us to construct and develop this system. We have several observatories in Blagoveshchensk, in Tunka near Baikal Lake, Ural near Moscow, in Kislovodsk and Argentina. These positions of telescopes are not by chance. For example, if you start to observe GRB in this point and night finish, you can continue to observe this object in the more western observatories, for example, in Kislovodsk. We work in 2 regimes, in alert regime and synoptic. We can receive alerts from gamma ray observatories, then point on it and carrying out synchronous multicolor or polarimetric observations of gamma ray burst prompt emission. All other time, when there is no GRBs, we work in observing regime and search for new objects and flashes. So in each observatory we have 2 tubes, 40 centimeter telescopes, and very wide field cameras. For now in Argentina there are only very wide field cameras. In each telescope we have a universal photometer with B, V, R and I filters realizing Johnson-Cousins systems and polarizers. Here you can see our photometer. In these slots you can establish your filters or polarizers. So as you can see on each tube we have 4 filters, and we can observe without filters in white light. So such construction makes our telescope is only a landscape instrument in the world that can observe the polarization. In July 2011, our polarizers were replaced by new broadband polarizers manufactured using a linear conducting nanostructure technology. Here you can see the transmission curve of our polarizers, wavelengths in angstrom and transmission in percent. So they have an excellent performance from ultraviolet to infrared region. We have on each telescope, as I said, we have two tubes, and in this tube we have two mutually perpendicular polarizers. In Ural and Blagoveshchensk, we have polarizers that are oriented under 45 and 135 degrees to the celestial equators, and in Kislovodsk and Tunka at 0 and 90. In Kislovodsk, we have an additional pair of polarizers under 45 and 135 degrees to the celestial equator. So, using only Kislovodsk telescope or Blagoveshchensk and Tunka telescope in pair, we can obtain the polarization degree and position angle for source. Unfortunately, in spite of the fact that in each observatory we have absolutely similar telescopes with similar CCD cameras, photometers, and other devices, there is a difference channel response between each tube and each telescopes. That's why we should make our tube equal. So we can, when we make a photometry, I mean, so we cannot use for calibration standard unpolarized or polarized calibrators. I mean, stars with a high level of polarization, because when we equal our tube, we kill the polarization of nearby stars and we kill the polarization of polarized calibrators. So there is a question, how should we calibrate our polarizers? We need something bright and something with a high degree of polarization. Fortunately, in the nature, there are another objects. It's BL-Lacerti objects. In the period of activity, they can have a very big brightness and show a very big polarization degree. So they are very suitable for master polarizers calibration. But from the other side, blazars, they are very variable. So we need another telescope for carrying out synchronous observations with this telescope and then comparing our data with their data for calibration our polarizers. So we have set up a collaboration with a group from St. Petersburg who leads a program of monitoring blazars. So we can calibrate our polarizers. Actually, we observe several BL-Lacerti objects, but I'll show you. The first object is OC457. This object showed a big activity in the beginning of this year. Its brightness in our filter went up 50-fold. We observed this object during 3 days in Kislovodsk and Blagoveshchensk, but due to the bad weather conditions in Kislovodsk, we have synchronous data only for 1 day. In this day, the magnitude of this object was about 15 magnitude, and we determine. So, as you know, polarization degree and position angle can be expressed in terms of Stokes parameters. It's only for linear polarization, of course. So we found Stokes parameters for this object and construct Stokes diagram. Here it's a blazar, and we also calculated the polarization of nearby stars. Of course, the dispersion, these stars near zero, was included in final errors of this object. So we also construct residual flux differences as measured through the polarization filters. Here it's a difference between intensity at a certain position of polarization angle and total intensity divided by total intensity. Here we have 6 points because we mixed 2 observatories, and this point is the same, it's just for plotting. So we obtain we found polarization degree and position angle for this object, and compared our data with St. Petersburg group, and this result was an excellent agreement with their result. And one more object with this name. This object showed a very high activity 2 weeks ago, and we observed it only for 1 day, but in 3 observatories in Kislovodsk, Tunka, and Blagoveshchensk also construct residual flux differences for this object and Stokes diagram. You can see that the polarization degree is very high. So here there is images from 2 tubes from 1 telescope in Tunka, and you can see that the effect is a naked eye. Blazar is here, and in this tube it more brighter than in this. So you can see this 30%. And now I would like to say some words about our polarization measurements of type 1a supernovae. As precise standardizable candles, type 1a supernovae led us to the discovery accelerated expansion of the universe. But in spite of this fact, there are some uncertainties. First of all, there are some uncertainties in mechanisms of explosion. There are 2 main mechanisms of type 1a supernovae explosions. Double degeneration mechanism, it's a merging mechanism, merging of 2 white dwarfs, and single degeneration mechanism, it's an accretion mechanism when burst is a result of a matter accretion in binary system from the star companion on white dwarf. So we think that in the first case case, the specific angular momentum should be higher than in the second. It should lead to the anisotropy of explosion and consequently to some polarization. So it will be independent measuring polarization, I mean finding some polarization, will be independent argument for this model, for example. Here I try to collect all significant polarization measurements of type 1a supernovae. Excuse me if I missed something. First of all, I would like to say that continuum polarization of type 1a supernovae is very low, and it's maybe there is some polarization in lines. You see that continuum polarization for supernovae 1999 BY was only 0.3, 0.8%. For this supernova, for example, it was only 0.4%. But it's very important to measure polarization before the maximum light, when the envelope of supernovae cannot expand. After maximum, the polarization is disappeared. For example, for this supernovae that was observed 21 days after optical maximum, no polarization was detected. For type 1a supernovae, we see some polarization, 2, sometimes 3% in lines. But we shouldn't forget about interstellar polarization. Interstellar polarization in our galaxy and in host galaxies of supernovae. We can measure interstellar polarization in our galaxy using empirical Tsiolkovsky law, but we cannot say that the polarization in the dust structure and dust distribution in host galaxies of your object is the same as in our galaxy. This supernova 2006X is a very good example and it shows that we should correct our data for interstellar polarization. You can see that in some lines polarization was near 8 or 2%, but after a correction for interstellar polarization, it was only about 1.5%. So I would like to stress that the polarization measurements of type 1a supernovae, the number of polarization measurements is very low. And the number of polarization measurements before the maximum light is much less. That's why we try to measure, I mean in our project, we try to measure the polarization of type 1a supernovae. But after this bright supernovae, we have another very bright supernovae, 2012 BH. It was discovered by Pan-STARRS Deep Sky Survey 2 weeks before the maximum light. And we observe this supernovae also before the maximum light. Here you can see the image of this object from our telescope in Master Tunka. We observe these supernovae in 3 observatories in Tunka, Blagoveshchensk and Kislovodsk. But weather condition was very different for all observatories in every day, in each day. No significant polarization, no positive polarization for this object, and before maximum light was found. The polarization was within our errors. So we summarized all polarization data for each day from all observatories and find that polarization was less than 2.5%. Of course, it's our accuracy cannot allow us to measure such values of polarization. But as I said, the number of polarization measurements is very small. So maybe it's like a selection effect. So we cannot say that for type 1a supernovae, polarization is near zero. And as I said, GRB's prompt observations will be discussed tomorrow for my colleague. I only want to say that we observe prompt polarization emission for 3 GRBs. But we observe each of these objects only by one telescope. So we have only a lower limit for polarization, because we observe each object only in 2 polarizers. For finding polarization degree and polarization angle, you need 4 observations. So we have only a lower limit. And what?
Upper limit, not a lower limit.
What?
Upper limit.
No, so upper limit. No, not lower limit, because you also can say that real polarization plane of object lies under 45 degrees to your polarizers. You see? For this object, we obtained that polarization was near 2% in 2 polarizers. And you cannot say that it's absent of polarization, because you can say that, okay, you observe this object in these polarizers and in these polarizers, but real polarization plane lie under 45 degrees. You understand? So it's not an upper. So we detect 2% of polarization, but it's yeah, but it's our accuracy. So the errors of nearby stars, the polarization, I mean, of nearby stars was the same. It was about 2%. So it means that we have not observation of positive polarization. Yeah. So no, but so we see then an absence of polarization, but it doesn't mean that polarization is absent. Maybe it lies under another
side of errors.
Yeah. As I said, you always say that the polarization play is another position.
But then you cannot say you have a lower bound. A lower bound means coercivity. That means, you know, something is at least 2%. So it's a mathematical. I think I understood what you meant, but.
So, and one word about future. We are planning to establish MASTER 3 telescope with aperture 1 meter, and in this telescope we are planning to have rotating polarizers, so the problems of calibration is disappeared. And I want to conclude that the observations of very bright blazars object shows that we can to measure polarization more than 10–15%. The accuracy of our observation is not enough for low polarized objects such as type 1a supernovae. They have really such low polarization, and if gamma ray burst happens, we are able to resist the GRB's polarization if it exceeds 10%. Thank you for your attention.